You took this pretest last week, and you had two books, A and B had a greater mass than A. And you had this question. The force exerted by string 1 on book A is less than, equal to, or greater than the force exerted by string 2 on book B. Tell me again how you answered that. How did you vote? Okay, last call. Oh, again, we're all over the map. Now, this particular pretest I have done a lot of research on. I used to collect them from every class until I got a great big mountain of these pretests. And then I poured through them one at a time, trying to find out why people were getting this wrong. What mistake in their reasoning were they making? And what I found was that there were many, many different ways to get this wrong. And it was discouraging to me. I was thinking, man, everyone gets it wrong for a different reason. And then I started to see a pattern. I found that if a pretest had a free body diagram on it, that person was almost always going to get it right. If the page did not have a free body diagram on it, that person was going to get it wrong for any one of many, many reasons. It's hard to even keep track of all the reasons, but you're going to get it wrong. So let's draw a free body diagram. Well, a free body diagram of what? Well, normally I'd draw a free body diagram of everything with mass. But in this case, I'm trying to compare the tension in string 1 to the tension in string 2. So it makes sense to draw a free body diagram that has both of those forces in it. Which book is acted on by both strings? A. So if I draw a free body diagram for book A, I have a weight force down, earth on A. I then ask, are there any magnets? No. So what touches A? Well, string 2 pulls back. I'm also told that string 1 pulls forward. And what else? Whoa, the floor. The floor touches and it pushes. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force, and in this case we're told there is a friction force. It's kinetic friction by the floor on A. And that's my free body diagram. Well, that's not helpful. It's not helpful until I use the fact that the books, both A and B, are speeding up to the right. So they have an acceleration to the right. That means this diagram that I just drew has to scream to the right. That means this tension force by 1 on A has to be bigger than the tension force by 2 on A, plus the friction force of the floor on A. It's got to be bigger than these two combined. And so that tells me that the tension by 1 on A is greater than the tension by 2 on A. Well, folks, that's not what was asked. What was asked is, how do I compare the tension by 1 on A to the tension by 2 on B? Well, if I want to do that, I have to know how these two forces compare, 2 on A and 2 on B. How do those compare? Equal. They have to be equal. By what law? It involves both the second and the third law, but we're going to call it the Law of Massless Strings. In this class, we're going to have a Law of Massless Strings. And that law is just that if it's a massless string, I got to have the same pole at both ends of the string. Okay? Now, if this is bigger than that, and that is equal to that, then this has to be greater than that. So the tension on book tension in string 1 on book A is greater than the tension by string 2 on book B. So the correct answer is C. 35 of us got that. Okay. I hope that everything is just coming together and it's starting to feel really good. I also hope that Christmas will be here soon. Okay. I go down to Home Depot and I get 3 identical, completely identical cinder blocks. And I hang them using massless strings as shown. And the question is, how do the tensions in the string compare? The tension in the left string is less than, equal to, or greater than the tension in the right string. So tell me with your clicker what you believe. Okay, that's all of us. The answer is equal to. Okay? And these problems are best answered with a free body diagram. If I draw a free body diagram, and I assume, I'm making this number up, that the weight of this cinder block is 50 newtons. There's no magnets in this problem. The only thing touching the cinder block is the string, and it pulls with a tension force. Now that block is just sitting there, which means it has 0 acceleration, which means its diagram has to screen balance. And my question is, which cinder block did I just draw the free body diagram for? All 3. And so the 2 strings have to have exactly the same tension in them. Now, some of you are saying, but wait, Greg, this one's got 2 blocks pulling on it, and this one only has 1 block pulling on it. Well, the answer lies in how we define tension. If you take a rope, say that rope is supporting some mass. If I take that rope and I break it and I put in a spring scale, the tension is defined as the reading on that scale, or how hard each part of the rope is pulling on its neighbors. If you think instead of a rope, a chain, it's how hard each link of the chain is pulling on its neighbors. Now, suppose I had a spring scale, and there's the hook, and I hung on that spring scale a fish that was caught. I didn't catch it, I don't fish. Okay, but someone caught it. Okay? And let's say that the reading on that scale is 3 pounds. Okay? Now I'm holding it, I'm holding the scale. In order to hold that scale up, I got to pull up on the scale with 3 pounds while the fish is pulling down with 3 pounds. But the reading on the scale is just how hard we pull on this hook, not how hard you're pulling up on the handle. And so the reading on the scale would be 3 pounds. Now, if I go here and I look at this string here, that string is not moving right there. Now, whether that string is not moving because I've got another block pulling down, or whether I've tied it to the wall and the wall is pulling on it, it doesn't matter. I get the same result either way. And so the tension in both of those strings is exactly the same. Check to see if your neighbor believes that.